Hey everyone, welcome. Today we're going to do a quick flyby of Chapter 21, diving into the awesome world of organic chemistry. Our goal here is to connect all the dots, the key terms, the main ideas, and see how they build the literal chemistry of life. So, let's jump right in.
So, here's our game plan. We'll start with why carbon is the undisputed star of the show. Then, we'll get our terms straight with some essential vocabulary. After that, we're going to build from the ground up, starting with simple hydrocarbon skeletons, and then adding in oxygen and nitrogen to make things interesting. And finally, we'll tie it all together to see the big picture.
So, first things first. Why a whole chapter on this? Why is organic chemistry such a big deal? Well, it all boils down to one single element: carbon. Its ability to form these incredibly strong and stable bonds with itself and with other elements is what creates the insane variety of molecules that makes life possible.
And this isn't just a small thing, it's fundamental. It's why we talk about carbon-based life. From the tiniest microbe all the way up to us, every living thing is built from a framework of carbon compounds. It's the universal blueprint for life as we know it.
You know, for a long time, there was this idea called vitalism. Chemists actually believed you needed some kind of magical life force to create organic molecules. But that all got turned on its head in 1828. A chemist named Friedrich Wöhler managed to make urea, an organic compound from totally non-living materials. And just like that, he proved that the chemistry of life follows the exact same rules as all other chemistry.
All right, before we go any further, we need to make sure we're all speaking the same language. The next few slides are going to hit the key terms from this chapter. I really recommend you pause on each one, read through the definitions, and just let them sink in.
Okay, here's our first batch of words. You'll see our basic hydrocarbons right away: alkanes, alkenes, and alkynes. Now, for alkane, you'll see it mentions single sigma bonds. That sigma refers to the strongest type of covalent bond, which is what gives alkanes their stability.
In this next group, we're bringing some new players to the field, mostly oxygen and nitrogen. Now, one term I want you to really keep your eye on is carbonyl group. That carbon double bonded to an oxygen, it's a super important structure that we're going to see again in just a minute.
And our final set of terms really helps us describe how molecules are built and changed. The two big ones here are functional group, that's the reactive part that gives a molecule its personality, and substituent, which is just a fancy word for any branch or group that takes the place of a hydrogen.
All right, now that we have the language down, let's see how it all works. We're going to start with the simplest organic compounds of all, hydrocarbons. They're made of just carbon and hydrogen. That's it. Think of these as the bare-bones skeletons for pretty much everything else.
And the simplest of the simple are the saturated hydrocarbons. Now that word saturated just means the molecule is totally full of hydrogen atoms. Every carbon has the maximum number it can possibly hold, and there are only single bonds between the carbons. These are our alkanes. This table gives you a great side-by-side look. Alkanes, like we just said, are saturated, all single bonds. Then you've got alkenes and alkynes, which are called unsaturated. That's because they have at least one double or triple bond, meaning they could technically hold more atoms.
And then, we've got this special class called aromatic hydrocarbons. These are different. They form stable ring structures, and their electrons are shared around the whole ring, which makes them incredibly stable. Benzene is the classic example you'll always see.
Okay, this is where it starts to get really cool. We take those basic hydrocarbon skeletons and we start modifying them. We can think of most organic compounds as just derivatives of hydrocarbons where we've swapped a hydrogen for something more interesting. First up, let's add some oxygen.
And that brings us right back to this critical idea of a functional group. This is the action-packed part of the molecule. It's a specific little cluster of atoms that determines basically everything: how it reacts, what it does, and what family it belongs to. Now, two of the simplest families that have oxygen are alcohols and ethers. Alcohols are easy to spot. They have that hydroxyl or OH group. Ethers, on the other hand, are defined by an oxygen atom that's sandwiched right between two carbon atoms.
Hey, remember this guy from our vocab list, the carbonyl group? This carbon-oxygen double bond is an absolute powerhouse in organic chemistry. It's like a central hub that serves as the foundation for a whole bunch of other important families.
And here they are, the big four built around that carbonyl group. What's amazing is that the only difference between them is what's attached to that main carbonyl carbon. If it's a hydrogen, you get an aldehyde. Two carbon groups, it's a ketone.
A hydroxyl group, that makes a carboxylic acid. And an oxygen attached to another carbon group, bam, that's an ester.
So we've seen what oxygen brings to the table. Now let's expand our molecular toolkit even more by throwing nitrogen into the mix. Adding nitrogen to our organic framework opens up two more essential families of molecules. These two major families are amines and amides. Now, they sound alike, and the key difference is super subtle but really important. It's all about what the nitrogen is attached to. In an amine, the nitrogen is bonded to just a regular carbon in the framework. But in an amide, that nitrogen is bonded specifically to a carbonyl carbon. That one small difference completely changes their properties.
Okay, deep breath. We've looked at all the individual pieces, the hydrocarbons, the functional groups, all the different families. So for this last part, let's zoom out and connect all these concepts to see the beautiful, overarching logic of organic chemistry.
After seeing all these terms and families, you're probably asking yourself this exact question. And yeah, it can seem really complex, but the basic idea behind it all is actually incredibly elegant and pretty straightforward.
Honestly, the core logic of this entire chapter boils down to these three simple steps. 1, you start with a basic hydrocarbon skeleton. 2, you swap out a hydrogen atom and plug in a functional group. And 3, that new functional group is now the boss. It dictates how the molecule is going to behave and what its name is. It's a beautifully simple modular system.
So I'll leave you with a final thought. We've just covered the building blocks. Now think about the world around you. Plastics, medicines, the clothes you're wearing, soaps. It's all organic compounds. So considering all the families we've just reviewed, which one do you think has had the biggest, most essential impact on our daily lives? It's definitely something to think about. Thanks for joining me for this review of Chapter 21.